right. Aloha students. This will be your final lecture of Geography 440 and kind of a range of topics, but just get started with it. Okay, hopefully you can see that. Meme searching. There we go. All right, so this. All right. Great. Well, hello, and thanks for coming. I guess I should address the fact that I don't have any hair anymore. It's kind of like the end of the pandemic. It feels like it's coming to a close, at least here in the US, and decided to cut my hair. I hadn't cut my hair for like almost 2 years, and it was getting to be a little bit oppressive. And also my wife was sick of it, so she told me to get it off, which is good. It feels kind of symbolic, like losing all your hair, and feels like a bit of a new start, which feels nice at the end of a long quarter, at the end of a long year. So anyway, I hope you all have something that you can do kind of at the end of this year that is sort of symbolic, that sort of, helps you sort of reset mentally and all those things. It's important to have those things in your life. But anyway, on to GIS. So the last lecture I usually like to dedicate to, bigger topics, bigger ideas, things that are new, that are exciting, try and get you kind of excited about GIS, the geospatial industry, the future of GIS, future remote sensing, places to go after this, basically. Your undergrad experience is really just kind of scratching the surface on really all topics, even your major topics, and there's a lot more to learn, as you will know. So yeah, with that, we'll get into it. All right, so basic outline, talk a little bit about what data science is, and look at BigQuery in GIS as a Google tool. It's kind of geared towards large databases and spatial information. Looking at some kind of fun trends in remote sensing, GIS as well. Talk about OpenGIS, talk about opportunities, and then I always kind of like to wrap up my talk, my classes with a little pep talk. Just give a little general life advice. It feels a little weird doing that asynchronously in my garage at 6 in the morning, but the lessons are still salient, so it's important. All right, so data science is kind of a fun one. It's sort of this, like, I don't want to call it a buzzword because it's real, but it's one of these terms that's sort of come into the sort of the collective lexicon recently. And in many ways it means the same thing as like data analytics and data engineering, and there's all these other terms for it. But data science is now sort of the hot term, and it's a really widely searched term on things like job websites, and employers are looking for quote data scientists and that kind of thing. So it sort of depends on who you ask, like, what is data science? It really depends on who you're asking. But usually we're talking about large data sets, right? So you're not dealing with a regression analysis of 100 data points or something like that. That's not really considered data science. Like, data science is often paired with things like data mining and getting into large, like, online data sets in particular, but it doesn't have to be online. So, it's one of these things. It's like, what does data science even mean? We've always had data and science. What is this new data science thing? And really, you should do a little bit of research online and look for, quote, data scientist jobs. Also, I say this all the time. I say data. It's supposed to be data. And I always correct myself, and I'll use both versions of that in the same sentence because I catch myself. But my PhD advisor always would get you. It's like, it's data, not data. Okay, so just so you know, but it's really looking at large data sets with new techniques, and a lot of the techniques oftentimes are things like machine learning and quote AI and stuff like that. And so using kind of these large statistical analyses to mine through stuff that you wouldn't be able to do in, say, Excel or something like that. So it's kind of like higher level large data analytics, etc. Okay. So the data science power couple, and this is sort of largely as I see it, but it's not entirely me. There are a lot of other people who think this as well. Learning two tools in particular can really help you with data science. And what you'll notice is if you go into, a computer science department, a lot of the intro classes are taught in Python. And Python is nice because it's sort of an elegant language. It's relatively simple to read and write. And it can do a lot. So you can, you can do almost anything with Python, including GIS. But then there's also R. So R is a statistical computing language. It's really popular with statisticians. So if you go into a statistics department, a lot of statisticians use R. And I like this superhero comparison that they made here, where like R is like Batman, where it's like a detective. It's kind of cunning and like clever and that kind of thing. Whereas Python is like more like Superman, where it's a little bit more like brute force and just like strong. So in my own research, and I was told this by basically when I was at working at NASA, like what they told me is like, do all of your analysis in R, but get everything ready for your analysis in Python, basically. So I took that to heart, and those are the two languages that I learned, and really the only two languages that I know. I try to stay away from the other ones because I just don't like learning new languages. But GIS is really nice because you can do a lot in Python. You can script in Python, and you can get all your data ready. And then what I generally will do is I'll export large tables or my data sets from Python, and I pull them into R, and then I start doing my stats on them. I can do analysis. I can make figures and visualizations and that kind of thing. So this isn't true for everybody, but a lot of people feel this way about these two languages. And if you're thinking of going into some sort of data science field, or you want to go get your PhD, or even just be kind of an amateur scientist, or your job might require that you do some data analysis, I would learn these two skills. And there's a lot you can learn with free resources online. You don't have to be a statistics or a computer science major, and in fact, don't be intimidated by them, because there's a lot of interesting things that you could do at a very low level with both of them. And I actually consider myself to be sort of a low level user of both of them. I use them when I need to use them for stuff that I need to do, but I'm by no means amazing using either of them. I'm always looking stuff up, like even basic syntax is just like something that I have to look up all the time. And it wasn't part of my undergraduate education. So like as an undergrad, I was a physical geography major, and that just meant that I, got a Bachelor of Science. I took a little bit more science, but like it did not really mean I took one class in MATLAB, and it just didn't, programming wasn't part of my education. Basically, I had to learn this all later, and I learned it kind of through a backdoor, through Model Builder, through doing GIS, and needing to like do a bunch of GIS things a bunch of times. That led me to sort of learn how to script in Python. And then once I had all this data, I needed to know what to do with it, and I couldn't do things in Excel. So I had to do them in R, basically. So it was born out of necessity. It's not like I came out of undergrad and was like had all these skills. It was very much learned like many years later. So I'm just trying to like put it out there for you. These are really valuable skills, basically. And if you put them on your resume and people see them, they'll take note, right? And you don't have to be from one of these STEM technical majors to have these skills. You can build them over the summer, right? You can take online classes, free or paid, and get these little certificates and that kind of thing. And that will really help you professionally. So I'm just trying to help you kind of get ready for that. And also it doesn't seem like they're that fun. It seems like they're really hard and that kind of thing. But when you solve problems using these tools, it's really gratifying. And I'd say it's much more gratifying than when you do like a tool in ArcGIS and it works, right? It's like, okay, that worked. That's nice. I have a map. But it's like when you're trying to script out a problem and you can actually work through it from start to end and you get the result that you were looking for. It's a very gratifying process. So yeah, so learn them. Okay, so here is a really interesting tool, and there's a neat YouTube video on this website. The website should be in the notes. You can also just Google BigQuery GIS, but BigQuery GIS is basically this online cloud tool that Google offers. So basically what you do is you can link to large online databases, or you can put your own data up online, and it has, it's kind of like an SQL type of database querying engine, and it's meant for big data, and it has new functionality, including this kind of geography function. I think that they did like a query on Stack Exchange or something like that, or GitHub, I can't remember, but it was like 10% of all these SQL queries have some sort of location information involved in them. A lot of people using these things, really need to know where things are, where customers are, where, census tracts are, whatever. So a lot of these queries involve location. And so BigQuery GIS was really geared towards those people, like, how do we bring space into these large, data analysis questions? So I would check out this website and check out the video just to sort of see what it is. Also, if you're interested in it, you can do a lab. They have a tutorial. Yeah, it helps you just like kind of pull in some GIS data, see how you deal with it in this kind of cloud environment, visualize it, and then query it, right? So, things like, you have a big table and there's lat longs, right? How do you turn those into points on a map? How do you run queries against it? I want to run spatial queries, right? Like your select by location in ArcGIS Pro can be done, in BigQuery GIS. Give me all, McDonald's locations within 10 miles of this subway station, whatever it is, right? All that stuff can be done in either platform. And then they have kind of their own tool, this BigQuery GeoViz tool, basically, that sort of allows you to visualize it and look at it and that kind of thing. So I would recommend you take a look at this if you're interested in kind of big data analytics. It's, again, another thing that you can put on your resume. Like, I know, I've done some basic BigQuery GIS stuff, and it could be as simple as one tutorial. I'll talk more about like you're building your resume and that kind of thing. Just having a real, cursory touch on a topic can warrant putting it on your resume. You don't have to be a master of this to say that you have some experience with it, and it could be a lab in a class, right? And that's kind of why I encourage you to try some of the harder labs in the class, because it's like, you're just trying to get an interview, right? You're just trying to get into that interview where somebody can talk to you and hopefully they like you, and and then you can elaborate and be like, well, I'm not like really that great in BigQuery GIS, but I've played with it. I did a lab in it. I liked it, that kind of thing. And, again, like, it's just a line in your resume. It doesn't have to be a line. It's just like a little phrase, a little tag in there. And that can be enough to catch somebody's attention. So, that's why we're doing these classes, basically. And that's kind of why I give you the leeway and the latitude to pick your own labs, as opposed to curating kind of what I think you should be doing. Here's another BigQuery GIS tutorial. Check them out. I haven't actually done them myself, but they look good, and I heard some good reviews about them. So and I've worked with a number of students who are using this, and it looks really powerful, and it looks like the future, basically. That's kind of why I'm telling you about it. Okay. So I really love GIS, as you probably know, but I loved remote sensing more. And a lot of people are sort of like, what is remote sensing and GIS, right? A lot of times they're put together, remote sensing and GIS. It's almost like it's one word or something, right? And I'm often asked, like, what is remote sensing? I know what GIS is, right? GIS is ArcGIS and QGIS and putting all this stuff into a map and overlaying it and, doing these spatial analyses. But what's remote sensing exactly? And remote sensing is really, sensing the Earth remotely, but it doesn't have to be the Earth. You can, like medical imaging is technically remote sensing, that kind of thing, right? But it's a term that was coined, I think, back in the 70s and really applied to like Earth remote sensing. And it's gotten really quite interesting. And there's a lot of new sensors out there. There's a lot of private companies who are getting involved in this space. There's a lot of great tools to analyze remote sensing data. My postdoc advisor is a woman who got her PhD, I think the year I was born, which was 1983. And, she would tell stories about getting Landsat data. Landsat's like the longest running, imaging satellite system, Earth imaging satellite system, that had like public data. You still had to pay a bunch of money for like one scene of Landsat data, because it was like processed and stored on like some disk somewhere, had to be like shipped to you. And then, she would tell us stories of like having to go to the computer room, where the room is the computer. The computer's that big to process this like one satellite image, right? And things have come so much further than that. Now we're dealing with these cloud platforms where you can do this analysis in a matter of seconds and do it dynamically. So over these large time scales, you can integrate different sensors, that kind of thing. Not to mention the options that we have now in terms of remote sensing data are really quite amazing. So remote sensing is, I often say it's like the base maps that we do GIS on. So it's all the stuff that we put into GIS, but it's more than that. There's a lot you can pull out of it, and it really depends on what you're looking at. But it provides a look at the Earth, and I think remote sensing and GIS, they're used together so much because they're kind of like two sides of the same coin. Like, I wouldn't really like GIS as much if I didn't have remote sensing, because remote sensing gives you something to look at and analyze. And remote sensing would be tough to use if you didn't have GIS, because it's in space and you need to be able to organize it, and you need to be able to turn it into vectors or analyze it for certain things and look at bands and do math and all of those things. And so remote sensing and GIS are really, they're bedfellows. They're very tightly coupled with each other. Now that said, you can do pure remote sensing and you could do pure GIS, but most people don't. Most people are kind of like bringing them together and doing a little bit of each. So anyway, the only issue with having all these new remote sensing systems is that there's almost too much data, right? And Google Earth Engine is really the epitome of dealing with this too much data problem, basically. And so they host, I think they told me last year that it was like 45 petabytes of data, which is an incredibly large amount of data. I'm not even totally sure how big that is. It's just not a real number to me, right? But they say like half of that is actually the Sentinel satellite system, satellite constellations, the European Space Agency. And that's a fire hose of data, and they're hosting all of it basically publicly for free. And that's great. But like, if you were trying to look at that yourself and you're trying to use like ArcGIS Pro and like download it to your desktop and do these like long time series analysis, like you would just bury your computer. You'd use all your storage, and it's sort of impossible. So Google Earth Engine basically said, don't bring the data to your problem. Don't download all of that data to your local computer and solve the problem on your local computer. Bring your problem to the data. The data is hosted in this massive data lake that Google hosts, and you can run queries there. You'll use their computational resources, their storage, their RAM, and then it spits you back the answer. You can download the answer, then you can play with that in ArcGIS Pro or QGIS or whatever it is. But it's this kind of paradigm shift in how we actually deal with big geospatial data, remote sensing data, because it just got too big. Like you just can't deal with it locally anymore, especially if you got like a little laptop or something. Like, not going to happen. So so this is sort of how we're dealing with this problem largely. But new satellites are being sent up all the time. They do a range of different things. And so remote sensing is really one of my favorite topics, because there's so much that you can do with it. And there's so much, in terms of different data sources, and different countries are putting them up, private companies are putting them up, that kind of thing. So it's a growth industry, to be sure. And not to be left out, AWS has their own Earth on AWS, which is sort of, they're just copying what Google Earth Engine is doing, basically. But, if you don't know this already, you might know, but like the internet runs on AWS, in that, I think like 70 to 80% of all, internet traffic is going through an AWS server somewhere. So even Google and Microsoft and Cisco and all these big internet companies, like they are actually renting space on the AWS cloud, basically, because it's cheaper for them to do it than to do it themselves. So, AWS built this infrastructure, and they built it out cheap, and they did it to sort of dominate internet traffic, basically, and sort of own it. So like they're already hosting all of this geospatial data for USGS or NASA or whoever's collecting, European Space Agency, whoever's collecting it. So they might as well make a system where you can go and query it, basically. And they sort of saw what Google did, and like, dang, that's a good idea. We should do that. And so they've done this, basically. So who knows? Maybe it'll replace Google Earth Engine at some point, but just sort of know that it's there. One of my good friends in my PhD program, he was a biologist, and he left academia. He got kind of disillusioned with it and the low pay and all this stuff, but he actually works at AWS on the cloud computation team. So Amazon, we hear a lot of things about Amazon, and it's good and it's bad, and what changed during the pandemic and online shipping, all this stuff. And so there's like the retail kind of online store, the Amazon store that most people think of when you think of Amazon. And then there's AWS, which is like the internet and computers and cloud computation, all that stuff. And he works in the cloud computation side of it. And he looks at like there's big days, Black Friday, Cyber Monday, whatever. There's all these like online deals, or like, there's particular points of like tons of internet traffic, and so he like helps to write the algorithms to like route all of that internet traffic through all like the nodes of the internet. Basically, it's kind of fascinating. To say what you will about AWS, but like all of this is kind of hosted on it, and so it's very much a part of the ecosystem, whether we like it or not. So just sort of be aware of that. This is something that's out there. It'll probably gain traction, in the coming years, because like Amazon's model is to just kind of like dominate everything, even if it's at a loss, and like drive away the competition. So they just want to get people like Google Earth Engine users onto AWS using it, and maybe at some point they'll charge you for it, but I don't think they do now. So just be aware that it's out there, and it's part of the landscape. All right, so there's lots of new satellites, and there's a lot of new satellites that I'm excited about. When I was doing my PhD, I worked at NASA JPL for a while, and I worked in the radar science division. And so it was really a fun place to work, because I was always around these scientists who were like designing these new satellites, and they were talking about, oh, there's this new one coming up, Calypso or CWIFs, or like all these like cool acronyms, and like they'll totally change the names to like have an acronym that sounds kind of cool. And so a good example of this is the JEDI satellite, and it's the Geosystems, Geosystems Ecosystem Dynamic LiDAR. Like, it's got investigation, like they totally have this weird name for it, so they could call it JEDI, and that's not an accident. But basically what they did, it's a laser sensor, it's a LiDAR sensor. We're mapping we're mapping the Earth from space. And there have been a couple, space lasers before. ISAT-2 and ISAT-1 were the LiDAR sensors in space before, but this one is really geared at looking at the forest. ISAT was looking at ice primarily, as the name sort of suggests, but it's this big piece of equipment that they basically launched up to the International Space Station, and they kind of bolted it on the International Space Station. And it's obviously using that a ton of power, because it's a laser, and it's just shooting this laser down at the Earth, and that has a telescope that kind of senses what comes back, basically. And this is actually what it looks like. It was created in Maryland, Goddard Space Flight Center. And I'm so excited about seeing data from this sensor, because they've been talking about it for a decade, like since I was starting grad school, and they've been testing it. So they have like these simulation lasers that they put on planes, that they put on drones, and they go map the Amazon, or they go map Greenland, or whatever it is. And now they've actually got it on the space station, and it's working, and it's producing data, and it's sending data back down to us. And we've got a couple of projects we're actually looking at. It's like, I'm really psyched about JEDI. It's like and they like, they're such geeks. They're like, ooh, may the forest be with you. That's like the motto of JEDI, right? This is like clearly like Star Wars reference, but like, this is just one of many, right? And it just happens to be the one that I'm really interested in, because I'm interested in forests, and I'm interested in vertical forest structure, and I'm interested in laser mapping. So like, this is like the genesis of all of those things. But like, there's a satellite for everyone, right? There's satellites that look at thermal sensor systems and heat, and SAR satellites are looking at reflected microwave radiation and that kind of thing. So there's a lot within the remote sensing world. I encourage you to sort of learn more about it. So this is kind of cool here. NASA has a plan to take the most detailed scans of the world's forest ever. So this is sort of this is largely for biomass dynamics. So they want to know where forest carbon is, so we can better estimate it, so we can preserve it, or maybe even have like afforestation projects where we plant more trees, and then try and monitor like how much carbon is being sucked out of the atmosphere and that kind of thing. So all this is really geared towards like carbon biomass dynamics type of projects. But yeah, this is just one of the sensors that can do it, but lasers happen to be really good at mapping vertical forest structure. And this thing's like on the International Space Station. Like, how cool is that? So, and one thing that does, which is I'll talk a little bit more about later, is that it allows you to like fix it, and and change it. And like, if something goes wrong, or like a piece of the sensor goes wrong, you can actually like go out and pull it off and put something else on, right? There's a robotic arm that can do these things on the space station, and that's not something that sort of happens on most satellite systems. And so it's one of the benefits to putting it on the International Space Station, is actually servicing it, which then can increase the lifespan of it, and the resilience of the instrument itself. I just recently heard about this company, and this company is really, it's exciting. It's cool. They actually are in talks right now with Cal Poly because they want to partner with academic institutions and do research and that kind of thing. Also, Cal Poly has a pretty robust engineering program you may have heard, and like CubeSat program and stuff like that, where we like launch these little satellites and do little experiments and that kind of thing. But it's this company called Umbra Space, and they're actually based out of Santa Barbara. And what it is they're high resolution SAR satellites, synthetic aperture radar, which is radar basically, or microwave, active microwave. And this has largely been the domain of governments, NASA, German Space Agency, Japanese Space Agency, European Space Agency. They're the ones who launched SAR satellites. There are some companies that do airborne SAR. So, put it on a Learjet, fly it at, 30, 40,000 feet and, go map the planet. And that also has occurred. But this is a company that's trying to do it from microsatellites or small satellites, basically. And it's pretty cool. So you can look them up and like watch this video and just sort of see like what their vision is. But it's neat. I just heard about them because they're in talks with Cal Poly and they want to partner with faculty and students and that kind of thing. And they're kind of local, right? They're from the Central Coast. So anyway, it's sort of an interesting company, and I think it's neat. There's another company called Planet, and I've talked about them a little bit, but Planet, they used to be called Planet Labs. And you should check out that second video. And they're doing similar stuff to what Umbra has done, and they did it first. I probably should have led with Planet, but they use these microsatellites, and they call them doves because they're satellites that are not meant for like military purposes, right? They're peaceful. That's the idea. They're instruments of peace. So that's why they call them doves. And you can see on this little satellite orbit map, you can see the little doves flying, right? So what I think is cool about this was started by a bunch of ex-NASA engineers, basically, who said, like, let's send up a bunch of these things, and they don't need to have this crazy spectral resolution. So we don't need to see all parts of the spectrum. We're going to see red, green, blue, and infrared, basically. And then we just send a bunch of them up because they're small, right? And they're like this size or something like that. And so you can send a bunch up because they're light, and then you basically just like have like they're in this bigger pod on a satellite, and you just like pop them out like one after another and put them in orbit and kind of like place them in orbit. And so the way it's been sort of described is it's like a string of pearls. So like there's one satellite and there's a satellite trailing it, and another one, and there's like a bunch in a line. And then as the Earth rotates, you kind of like get this like progressive coverage map. And what's cool about Planet is that they get a picture of the world every single day at about 3 meter resolution, 3 to 4 meter resolution. So that's not enough to like read your license plate, but you can, see a car potentially, or maybe not quite a car, but like a Big Mac truck maybe, right? And so, what's valuable about this is the temporal resolution and the fact that you get shots of the Earth every single day. It's basically like a video time lapse of the Earth. And so if something happens, there's a tsunami or a wildfire or, a big geopolitical event or, something happens, you can see it the next day. Like you can actually download this imagery the next day. And so it's just a total paradigm shift compared to things like Landsat, where it's like you had to wait 16 days to get an image. And so it's rapid, basically, what's kind of cool about it. So yeah, look up Planet Labs. They're a really neat company. They allow researchers to download a bunch of imagery for free. But they sort of provide data as a service, right? So private companies want to know stuff, government want to know stuff. It's like, okay, you can, basically sign up for a subscription or, buy individual images. I don't quite know how their pricing model works, but so yeah, anyway, smaller satellites are really increasing in popularity, and just like our phones have gotten progressively smaller, and electronics have gotten better and more compact, and all of these things, smaller is better, especially since it costs a tremendous amount of money to launch things into space. So it kind of makes sense as a trend. But everyone's getting into the game. I think this is like a Filipino science team who's like launching their first microsatellite. And oftentimes with the microsatellites too, it's like you just pay for some space on somebody else's satellite, and they just drop it where you want them to drop it in orbit, basically. And so this is something that's going on right now, and I think it's really important. And this sort of leads us to another topic, which is collision risk in space. And, humanity is launching a bunch of stuff up there. I've heard numbers like 36,000 pieces of debris or satellites or just stuff in orbit. And that's increasing kind of exponentially. You probably heard of Elon Musk's Starlink or whatever, like the internet satellites, where it's just like, there's gonna be thousands of these things up there that are providing like broadband internet, which is like, that sounds good. But there's also it's also space junk, and it gets in the way, and it was screwing up like space telescopes. Like these astronomers are trying to look out to space and study these stars, and then suddenly there's like all these streaks like running through their imagery because it's like all of the new Starlink satellites, right? And so this is a little bit problematic. As you can imagine, there's a bunch of junk up there, and it doesn't just like fall to Earth real quick. It's like, depending on where you put it, it can actually leave. It can actually be outside of the Earth's sort of gravitational influence and drift off into space, or it drifts back into the Earth where it falls into the atmosphere and burns up and that kind of thing. But that can take years, right? Decades, depending on where it is. So a lot of people have been talking about this and like, how do we deal with this? How do we clean it up? Can we clean it up? Can we reuse stuff? That kind of thing. Can we, all this stuff has a bunch of like precious metals and stuff in it. Can we actually like reclaim some of that? And so it's an active point of contention right now within the space and the remote sensing communities, because another issue is that when you get into space and you get outside of the Earth's atmosphere, you just get baked by radiation, right? There's not the same protection from X-rays and gamma rays and this high, ultraviolet radiation that is really bad for you, right? But it's also bad for electronics. And so when you get these sensors up there, they get kind of baked by radiation and they die quicker than they would if they were inside of our atmosphere, basically. And so not only are they up there, they're not even working. And that's a problem. Like, as long as they're gonna be up there, they should be taking pictures, or they should be providing us some information or some use, but they don't last that long, basically, is kind of what I'm saying. And so, there's a lot of interest in this term Star Wars, not the movie, but like there's a term called Star Wars where it was brought into sort of the public eye during the Cold War and under Ronald Reagan, basically. And, it was this idea that we'd be fighting wars in space. And also, like when, people were talking and really scared of nuclear weapons, you could launch nuclear weapons from space because you could hit pretty much anywhere on the planet really quickly. Fortunately, we don't talk about that so much anymore, but there are still issues in space and we're worried about it. And China actually just launched this missile to basically knock a satellite out of orbit and blow it up. And this is problematic for a bunch of reasons. One of the big reasons is actually that it creates these debris fields, right? When a rocket hits a satellite, it explodes, and there's all this debris that goes off kind of in all directions. And if it's in orbit, it's going, approximately 17,000 miles an hour. And all that stuff goes in many different locations, and there are many different sizes. There's, there could be like a big piece of space junk, but there'd be little stuff that's the size of a bullet, right? And that can do a ton of damage if it hits something like the International Space Station, for instance, right? And so, and at a certain size, we can't track it anymore, right? So there's a bunch of stuff out there that are like bullet-sized, projectiles going many thousands of miles an hour, and they're just going to wreak havoc, basically. So this leads us to this thing called the Kessler syndrome, or the Kessler effect, basically. And it's this theory, this NASA scientist, Donald Kessler, came up with this in the 70s, basically around the time we were talking about Star Wars, where there's this theoretical situation in low Earth orbit, in LEO, basically, where we've got this density of objects. There's too many things in low Earth orbit, and then you have a collision, and that collision creates this debris field, basically, kind of what I just described. If you ever saw the movie Gravity, that kind of happens. So there's a collision, and there's all this like debris and whatever. There's astronauts floating off into space, but the idea is that it creates this like ripple effect, this chain reaction where all the debris hits other stuff, and then that explodes, and that creates more debris, and it's just this like chain reaction. It gets worse and worse and worse. The worry there is that large portions of low Earth orbit could be kind of off limits because you've got too much debris and they're not usable. For generations, basically. This could last for a really long time, and it's a real worry, basically, and it's becoming a more and more real worry as we launch more stuff up there. And, again, our tracking systems aren't that great, but like if we have a big collision in space, that could really screw things up as far as, studying the planet remotely and doing environmental science and all that stuff. Like, I don't know what I would do for a job if we didn't have these satellites up in orbit. Like, I need them. And a lot of people need them, and we need them for a variety of reasons to, study the planet, study climate change, study carbon dynamics, et cetera. So it's kind of one of these scary things that needs to be talked about, basically. To that end, there is a lot of talk about modular satellite design, and this is sort of why JEDI is cool, is because like it's up on that International Space Station, but like, you could have spacewalks like this. Astronauts can go out there and like work on things. That's like a super dangerous thing to do, but like it happens kind of regularly. Also, there's like the robotic arms. Like there's a way to service them, basically. Usually when we launch a satellite up there, it's up there until it falls back to Earth, basically. We don't touch it again, even like long after it's dead, right? But, one of the things that people have been talking about is like, the modular nature of things. Can you pop out the battery system? Can you pop on a new solar panel? Can you, insert a new camera in and take things out? Could we have robotic satellites that have propellant on them that, you can steer through orbit and they can like catch up with satellites, service them, replace the part that doesn't work, and then let it go on its way and then continue its lifespan, basically. So, can these things be repairable in orbit? And the answer, I think, is largely yes. It requires a bit more planning, but that could be good because it would make, these whole systems more sustainable and cheaper, and there's less space junk and that kind of thing. So it's been talked about a bunch, and I think it's the way things are going. And it's also like why they're starting to put these things more on space stations, because if it's on a space station, you can control it a little bit more and you can fix it a little bit better and that kind of thing. And then, also you have it. So if it stops working, you can always send it back to Earth in a manner that could kind of save it and that kind of thing, so we can work on it on Earth. So this is sort of the way things are headed, and I think it's a really interesting kind of concept. So often called on-orbit servicing. But the idea is to make this less expensive. As you can imagine, these things are incredibly expensive, and like sometimes they go up and they don't work, right? And when I was a kid, you may have heard of this Hubble Space Telescope, basically, but we launched the space telescope, and it was supposed to be like this amazing telescope that was going to show us all these things about these distant galaxies that we could never see before, right? And it gets up there and like the pictures come back blurry, and it was something really stupid too. It was like somebody made like a unit error between like inches and centimeters or something like that, and just like it was blurry. It was like somebody just smeared Vaseline on the lens or something like that, and it was so expensive, right? Hundreds of millions, maybe billions of dollars to put this thing in orbit. And it was just a total catastrophe. Like, what do we do? And so they launched a mission basically with the space shuttle. We don't have it working anymore, but you probably know what the space shuttle is, and has those big bay doors on the back of it and a big arm. And it was this crazy operation. It was the first time it really ever been done, where they launched the space shuttle up to the Hubble Space Telescope. They opened the doors, they grabbed it with this arm. All of, a couple, like one or two astronauts like went up there, and they had trained for this for months, like in these massive tanks and their spacesuits and that kind of thing. And they basically had to like replace a lens on this big satellite. And they did it, and it worked. And then it produced these amazing images, and it taught us a ton about space. But it was just like somebody screwed that up in the design phase, and we had to deal with it. And it was so expensive that we couldn't just be like, screw it, we'll just launch another one. Like, we had to fix it, and we did. It worked, but it just sort of highlighted the fact that like, this is not a great system. Like, we need to come up with a slightly better system for this. And that's not an Earth observation satellite, that's a space observation satellite. But it's still a remote sensing satellite. Like, it's a similar principle to just looking out instead of in. But regardless, that's the way things are headed, because we can't send these things up and have them not work. All right, moving on from remote sensing a little bit, talking about the future of GIS. The way I see a lot of the future of GIS may not be the way everybody sees it, but I see a lot of this going onto the internet and going open, basically. And part of that is just, those are the larger trends in, the internet in general, and data analysis and data science is, how do we make these things open? How do we make these databases open? And then a lot of this is just like, right now we're tied to this model, this desktop model, right? And based on doing this class and other classes online, where it's like, you normally be in a computer lab where we have all these desktop computers and all the software, right? But like distance learning and COVID, it's like, well, you're at home, and I don't have the computer that is a $2,000 computer that has all this software preloaded onto it. Well, what do? Well, we're virtualizing it through the cloud, right? And so I think COVID really accelerated some of these trends that were probably going to happen anyway. They just made it happen faster. And and if you've taken any of my other classes this year, you know that it's been a bumpy transition because we weren't quite ready for it, basically. But it's the way things are going to head, because like a lot of people, for instance, have a Mac computer. Like I'm on a Mac right now, right? I'm virtualizing a Windows instance so I can run GIS like through a different computer that's sitting on campus. But I like my Mac, right? And like I like to use it and that kind of thing. But it doesn't run ArcGIS, so it's like, so am I just going to like base my entire computer choice based on like one software package? And a lot of people do, especially with GIS. But I think it's headed away from that, and you can already see it with ArcGIS Online. You can do a lot of like basic analysis on ArcGIS Online through the web platform. You don't need to have it on your local computer, that kind of thing. So I think that's very much the way things are headed. Also, when we have all these large data sets, you can't have them locally. So OpenStreetMaps and NASA imagery and planet imagery and all of these great remote sensing data sources, they kind of have to live somewhere else. So if they're already living somewhere else, why don't you just process them somewhere else, right? All you really want is the answer. So so this is very much the way things are headed. Also, the rise of mobile platforms, GPS chips and phones are getting better, which allow you to do much more interesting and accurate things with them. So cloud-based, open access is sort of the way I see things heading. Now that said, like ArcGIS is the 900-pound gorilla in the room. Like they're not going away anytime soon. I think they're the second largest publicly held corporation in America. So they make a ton of money, and a lot of people still use ArcGIS and ArcGIS Pro, now moving to Pro. But that's largely based on like academic decisions, and universities teach it. I teach it. Like pretty much anyone who teaches GIS in America and globally is teaching some form of ArcGIS. Now that's shifting a little bit, but because all the students come out learning ArcGIS, the governments and the companies, they also need to kind of buy into that, because that's the system that people know. So they're everywhere. Basically, it's sort of a ubiquitous GIS company, but that is largely changing because their pricing model it's a little expensive, basically. And when we're concerned about issues of digital equity and that kind of thing, that's a real concern. This is kind of a fun one, and I think it's kind of cool. Indoor mapping, basically. So traditionally, GIS has largely been the realm of the outside. Basically, we map things outside. Buildings are the realm of engineers and CAD designers and that kind of thing. But those worlds are now merging, basically, and we're using a lot of indoor GIS, indoor positioning systems. So GPS doesn't work inside. So you have to have these other systems to figure out like where you are in a building. And buildings are, incredibly complex, as you might imagine. This little schematic sort of shows you. But GIS allows you to map it, basically, and integrate data from CAD. Now, why would you want this? Well, maybe you're a building manager. You need to know where certain things are. COVID, responses, that kind of thing, like in the dorms. You have an outbreak. Well, where does it happen? Where is your HVAC? Where's all your air going? All of this stuff, right? And so there's a lot of real good reasons to have a good map of something. Like a consumer-facing application of this is like, I've been spending a lot of time at Home Depot recently, because it's like, other than teaching online, I'm just working on little home improvement projects or whatever. But it's like you go into Home Depot and it's like, okay, I have a shopping list of 3 things. Like I kind of know where they are. I'm not totally sure they are. So like, if you have that shopping list digital and you send it to Home Depot in advance, it's like, come in this exit or come in this entrance, go to this aisle, go to this aisle, go to that aisle. That's the most efficient route, and come out this exit. Check out here, go out this exit, right? And so it's a good way of routing you throughout your day, whether it be through Google Maps to like go to points on the map, or to like go to points within an actual building to go do certain things, right? And so you could think of like a nurse in like a COVID ward or something like that doing a similar thing. I got to go see this patient, I got to go pick up this medication, I got to go see this doctor, and I got to go see this other patient, right? And like that is a routing issue that traditional GIS hasn't really been geared to do, but indoor GIS is really picking up. Esri has something called Esri Indoors, and then there's also these other systems. You may have heard of this. It's called building information models. So, if you think about a skyscraper or something that's like, many stories and just has a ton of stuff in it, right? So elevator shafts and electrical and plumbing and insulation and, security cameras, and et cetera, right? The list goes on and on. There's so much stuff that goes into a building. So a BIM is a building information model where we put all this stuff into a model, right? And you make kind of a digital twin of your building, basically, and it allows you to, from the ground up in terms of designing the building, building the building, maintaining the building, improving the building, et cetera. It really helps to have these BIM models. And most buildings, especially like on the Cal Poly campus, were built in the time before these digital models. Basically, you just built a building and you just put stuff where you needed it, and that's that. But largely, especially with like the rise of the Internet of Things, the IoT, is like there's all these sensors and they're all integrated and they're all tied into the internet and they're providing information in these different data streams. And so a lot of that actually lives in what are called BIM models. So and then also like all the way to the end of the life cycle of the building, right? All the way to demolition. It's like you knock down a building, you better get all the valuable stuff out of there first, right? And like you need to know where it is. So yeah, so this is something that's kind of this new frontier. That's kind of a fun frontier in GIS. And I helped start a company that is in the Esri startup program that does just this. They do indoor mapping of buildings, and they do indoor remote sensing where they actually take LiDAR sensors into buildings. They scan the insides of it. They have cameras, like these ladybug cameras that like look everywhere. And then you can also put all these sensors onto these carts. Basically, the cart is kind of like geospatially aware. So you like take it outside, take a GPS point so you know where you are in geospatial space, and you go in the building, basically, and it has these IMUs on it, so it knows where it is, and it knows how fast it's going, and it has the wheels are like clocking distance, and so as you cruise around, it's just making a map, right? And you're collecting all this remote sensing information, but then you can also put other sensors on it. So like we put on these like Wi-Fi sniffers, or like banks of phones that are doing these like ping tests where they're just like, there's a Sprint phone, and there's a on a T-Mobile phone, I guess it's the same company now, and then like a Verizon phone and an AT&T phone, and they're doing all these tests like continuously, where it's just like, pinging the tower. Where's the closest tower? What's the signal strength? What's the signal strength? What's the signal strength? Like over and over and over again. And then like you fuse that with the location, and you can make signal strength maps inside of a building, or Wi-Fi signal maps inside of a building. And the possibilities are endless, right? You could put on something that measures radiation, right? Radiation actually gets like trapped in concrete. Concrete is like really good at holding radiation. So you want to know like where radiation is in your building, or you could have thermal cameras that tell you like, where is my building leaking heat to make it more energy efficient, etc. Like the list is really endless in terms of the things that you can do with this. And so, the rise of IoT is, really looking at these things and looking at all these sensors and these data streams, and how do we improve and how do we optimize and how do we make things more efficient and that kind of thing. And all of that kind of has a spatial component, especially inside of buildings. But not exclusively. So anyway, this is kind of exciting stuff that I think is kind of cool. And when people think of GIS, like large, like for me, it's just like Earth remote sensing, looking at ecosystem dynamics and stuff. But like it doesn't have to mean that at all. It could mean like looking at like radiation maps of buildings. There's like a totally different application for the technology. Like I said, OpenGIS is I think kind of taking off, and people are realizing they don't need to pay all this money to Esri. Leaflet is a good example. CartoDB are these like kind of open portable GIS applications online. OpenStreetMapper is a really good data source, kind of crowdsourced. Like I said, Esri is really deeply entrenched in academia. It's what students learn, so it's what they want to do when they leave school, but that's changing. More QGIS is being taught, and people are recognizing the value in saving money, basically. So the tools are getting better, the documentation is getting better, the user base is getting larger, and that's just going to continue going. In some cases, the maps are better, actually. This is kind of cool, actually. So you see like New York and Central Park there. OSM versus Google, OpenStreetMap versus Google, and people can add their own stuff, and that's the beauty of crowdsourcing. Now it comes to an issue of data curation, where like sometimes the data's not necessarily good, data is not necessarily good, but this is how you get a lot of stuff done quickly, basically. So yeah, it's kind of a neat thing. You should check it out. I like it because it's open, right? And a lot of people use this. So anyone who's got like an open map online, they don't want to pay Esri, just use OpenStreetMap. It's just as good, in some cases it's better. Here's an interesting article about it. A lot of times people have hackathons, right? Because it's like, oh, there's this random village in Africa that we want to go do some aid at. No one has any good maps. Well, let's pull up satellite imagery. Let's make some maps. Let's talk to people on the ground. Let's have them participate in making better maps for these places. And I think that's it's the way of the future. Something you've probably heard of a ton, but we haven't really seen much of is self-driving cars. The reason is because self-driving cars, like the level of accuracy needs to be almost perfect for these things to actually be implemented. Like we're much more willing to have a human make a mistake and get in an accident than we are to have a machine do it. And it's just part of like basic psychology. We just don't want machines making decisions and making mistakes, even if they're so much better at it. They have to be like, 100 times better than it. They have to be almost perfect at driving before we'll actually trust them. And there's obviously problems that can arise. You've probably heard of like these ethical problems, right? Where it's like driving, self-driving cars going down the road, a kid that comes out on the bicycle and the car can't stop in time to not hit the kid. So what does it do? Well, like on one hand, there's a cliff over here. I don't know why the kid is so close to the cliff, but the idea is that it has to make a decision, right? Does it kill you? Does it kill the kid? Does it run into this family over here? Like something's got to happen. And like, how does that decision get made? Like the ethics of self-driving cars are really complicated and not everyone agrees on them. And yeah, it's like, that's another issue, right? It's like when you have a driver, they have to make a split second decision. And we're usually much more willing to sort of accept those things than we are with self-driving cars, or something else, something autonomous, something non-living is making the decision. And that's really complicated. And that's what's, why we probably won't see these things on the roads in any sort of like large scale commercial sense for a while, until a lot of them are sorted out, basically. But it does seem like, this is sort of the future because it can make the road so much safer. A lot of companies are out there right now mapping the roads, with LiDAR, with photos, with GPS. They're laying the groundwork for sort of the digital infrastructure that is kind of coming. So this is a big growth industry in terms of GIS remote sensing as well. It's ground-based GIS looking at self-driving car infrastructure. This is kind of an interesting paper that looks about the ethics, basically, and how do we make decisions about this stuff. Okay, so something that I always tell my students is that, like, GIS is great for your career. It's a skill you can put on your resume. Also, even if you do GIS, very few people are like pure geographers where they just do GIS and they're just focused on GIS, or like, they work at Esri and they're just like working on GIS tools and they're helping other users. Most people who do GIS are doing something else and they use GIS as part of their toolkit, basically. So like for myself, like I love GIS, I think it's awesome, but like I probably wouldn't use it if I wasn't into like biological systems and ecology and remote sensing and like laser mapping of forests. Like that's what I think is cool, but GIS just happens to be the tool that helps me to do those things, basically. And that's really the way it is for a lot of GIS professionals. And so this kind of allows you then to like get into what you want to get into. Just use this as a tool, put it on your resume. It might help you get a job interview. I always tell my students, like, right out of college, I got a job making like $14 an hour, doing like half field work and half GIS, but I got the job because I could do a little GIS and I got paid like $1 an hour more than all the field techs who were just like, the field grunts who didn't really work on the computer. They were just out like doing the stuff. But I like doing that too. Like it was fun being on the field, but like occasionally I like to come back in the office and make some maps and that kind of thing. And like you got paid $1 more an hour. So anyway, oftentimes these interdisciplinary teams, they really need somebody who can handle spatial data, especially in like biology and in environmental science and that kind of thing. It's like, oh, cool, we have all this data, we got it in, and we have all these GPS points. Like, now what? Does anyone know how to make a map out of this, right? And like, oftentimes they don't. I had a student who graduated a couple of years ago, and now she's in nursing school, and she like sent me an email. I was just like, hey, Fricker, how do I use QGIS again? Like suddenly I care because like somebody needs to make a map. It happens all the time. My roommate in college is a lawyer, and he's just like calls me up like, dude, I need to like map all these parcels and figure out like I need to sort through which ones are zoned for this use and select these ones. It's a total GIS problem, right? And I was like, dude, download QGIS, download this data over here, run this query on it. And he was just like so psyched on it, right? So there are like lawyers who do GIS, right? And that's the point, is that like anyone in any of these fields occasionally needs to make a map. And on these teams, it's really nice to have somebody who has those skills, even if it's not the focus of your career or your job. So just mention it. All of these things, like all these new tools that you were doing on your lab, put those into like your skill sets on your resume. Even if you don't want to do them necessarily, it doesn't matter. It might help get you a job. And, it's worth putting out there. So another thing with the pandemic is that I think remote work is kind of here to stay largely, which is tough, especially in like an academic setting. And, I don't like teaching online. And I don't think anyone really likes learning online exactly. I think being in the classroom is a really valuable thing, but some of these things are really nice. Like I might still pre-record some lectures. I might still have Zoom office hours. Some of those things are really, really handy. And it also allows you to travel and be more free in terms of where you are. So, sometimes remote work can be really good. Other times it's problematic, but I don't think it's going anywhere. So, you kind of embrace it, but also, get a van, go drive across the country while you're working, pay for your gas, right? That kind of thing. So it's just an idea. This is kind of cool. So this is just a paper that was written about 10 years ago, just talking about workforce trends, geospatial workforce trends in the US. And this is, I wouldn't go and get this paper, but I wanted to highlight this last sentence here in the abstract, which is because of strong growth, an imbalance will remain in which demand outstrips supply, particularly in the more sophisticated modeling, design, and research positions in the geospatial workforce, meaning the more technical you are, the more in demand you are. So if you have some of these skills like R and Python, you can always have a job, basically, and you'll always have a better job. You'll always have a better paying job, basically. So, again, if I want to take it from me, like, this has been talked about largely in terms of larger trends in the industry. And this isn't just GIS. This is kind of, all things sort of tech related. All governments need some form of GIS, right? Whether it be local, SLO county government, or whether it be the US government, right? Or the UN, right? We need to know where stuff is to manage our resources, things like accounting for parcels being sold and bought and taxed, emergency services. Where's the fire department going? Where's the ambulance going? Planning, we're trying to figure out what to do with the next step in our city. Infrastructure management, the power grid in Texas being a good example, right? And then community engagement too, getting people involved. Everyone can understand a map, so that's a good way to reach out to people and that kind of thing. So one of my old students, actually not an old student, he's actually, I worked with him at the startup company, but he's actually an old Cal Poly student who was a geography student. He just got a job with Everett, Washington, and he's so psyched. And he just like moved up to Everett, and he got he's got a cushy government job now with benefits and that kind of thing. I don't think it pays great, but I think like it got good benefits, and I think he's really psyched about it. So a lot of government GIS jobs, and I think they're good jobs to get because of the benefits, and they take care of you all right. The other side of that is like the tech startup world, and I kind of been in both, and they're so different. And the tech startup one is like good to do when you're young and like maybe single and like can afford to lose your job, that kind of thing. But also like there's high risk, high reward. So you might actually get in on the ground floor of some startup that actually gets bought, and you can actually get equity in the company and that kind of thing, and maybe get rich, or like the government route, which is a bit more stable, a bit more even, and they're cool for different reasons, basically. But everyone needs GIS, and GIS sort of exists in both of these realms. This is kind of a cool one. So we got featured in the Esri blog, basically, and they just looked at our base mapping project. And so that's happening in this class, but it's been going on for years. And it also exists in the Natural Resources Department and in the city and the county. And so we kind of contributed to this. So there's a little story about this on the Esri blog here that you can look up, and it's kind of neat because it talks about like how the city government and collected all this data. They collected all this really nice aerial imagery, remote sensing of the county, and then they basically gave it to Esri, and now Esri is doing us a solid by hosting it because that data is really big. But then now we can use it to do things like improve our base map, or if people want to look at the Esri base map, it's much sharper, it's much clearer, it's aerial imagery, not satellite imagery. And so it provides a lot of things. Like one of the teams in our class had to go through and digitize a bunch of stuff on campus, like the new dorms, right? Things that weren't previously on the base map. And with this really high res imagery, it allows us to do a much better job of that, and that's just one example, but it's kind of a cool blog post if you're interested. Okay. The NGA, National Geospatial Intelligence Agency. This is basically GIS spies, essentially. And I've got a buddy who works for a contractor that works for the NGA. It's the type of thing like, hey, what are you working on? I said, well, I can't tell you, but if I had to tell you, I'd say that we're digitizing roads in North Korea using artificial intelligence, something like that, right? And like that's the level of things that are going on there. And a lot of people come through these programs and they really want to get into that type of work. I've had students who want to go work for the CIA and do this type of work. And some people don't want to touch it with a 10-foot pole, right? They don't want to be a spook, but it's really up to you. And there are a ton of jobs there, and there's a lot of applications for GIS and remote sensing in these type of industries, as you can imagine. So, whether you like it or not, it's there, and we use it all the time. Not academia, not research, not intelligence, but private industry. And this is probably where a lot of this stuff is, right? And this, we're just talking about business here, different private companies, startups, right? Business GIS is a big deal. Like, where do I put the next Walmart? Where do I put the next McDonald's, right? Where do I close stores like in a pandemic? Which ones are, serving certain populations, or they're not doing well financially or whatever? Marketing GIS, how do I like reach certain people, that kind of thing? Strategic planning, what are the next plans? Customer identification, demographic analysis, all sorts of different things. There's also just like a private industry that does surveying and mapping for local governments or for private entities or whatever. I used to work for a private LiDAR and mapping firm, and we would give Google data for their base maps, or we'd work for a local government or a university on one-off jobs where we just go map something. And there's their own industry there that is, that oftentimes are, data providers for people who use GIS, or they do GIS themselves, right? So a lot of interesting jobs just in private industry. You don't have to work with government if you do GIS, I guess is my point. Academic research, obviously a little bit niche, but I'm partial to it because I think it's really interesting. Most geographers, like geography professors in college, majored in something else. They're biologists or they're historians or they're anthropologists or something else, and GIS just happens to be one of those things. And then when in academic departments, when people get hired, it's like, we want a political geographer, we want a biogeographer, whatever it is, right? And so, have another focus. Like, don't just be focused on GIS. Have another focus that you use GIS for, basically, because when you get on these interdisciplinary teams, it's like, we need somebody who does GIS. So I work on a team with biology, with these biologists. I work with a computer scientist and an economist and a couple of biologists, and I'm the geographer. So when we have spatial information, we have spatial problems, like, I'm the one who deals with it, right? And so, interdisciplinary teams, interdisciplinary teamwork, and research. Like, research is very much a team sport, right? So, so you have to be able to work with people, and programming skills, like I said, Python and R becoming much more important. And don't get into this. Don't get into academia if you don't love the topic, because you'll spend a bunch of time and you'll be poor in grad school, and you don't want to do that for something that you don't love, basically. So also, don't go to grad school if you're not ready and you don't know what you want to do because you love that topic. So, if I'm talking about grad school, we can talk about that offline. If you're looking for GIS jobs, you're about to graduate, look at these websites. These are all good websites: gisjobs.com, GIS Clearinghouse. Esri's got stuff. You just look at like Monster or Indeed, or like the regular job websites too, and do that. Also, use a recruiter. Recruiters also called headhunters, right? And they go out and find you jobs, and the companies will pay them to like basically do quick searches or extensive searches on candidates to find good candidates. I recommend using recruiters. Actually, they do a lot of the work for you, which is kind of nice. So yeah. And of course, what GIS job website would be complete without a map? This is kind of a cool map, right? And like, maybe you want to go live in Europe, you want to go live on the East Coast for a while, you want to go live in South America. Like, you could search for GIS jobs based on location, which is kind of cool and pretty logical for a geographer. But I encourage you to travel also. This is the Esri website. It's kind of cool because it just like shows a bunch of different stuff, from helicopter firefighter to climate scientist, right? And all of them are using GIS. All right, the last little bit, and I've sort of been doing this throughout the talk here, but I give you a little bit of a pep talk and talk about a couple different things that I think that you should hear from me before we move on from this class. Failure is really important. Fail fast. You've probably heard that before, but it's like you have to fail to kind of hit these dead ends, know where the limits are, and then kind of reset and do it again, right? So fail often. Failure is a good thing. Embrace failure. Don't be afraid of it. Lean into that failure, and then do it quickly, and then reset and do it again, right? And like, that's how you actually make progress, basically. Inferiority complexes or imposter syndrome, you've probably heard of this, right? They're particularly common in liberal arts students. We don't see the computer science students having these imposter syndromes as much because they've got these incredible technical skills, but a lot of liberal arts students are like, I'm not good with technology. I'm not good with computers, right? I don't belong there. I can't apply for that job because I don't have any Python or whatever, right? And it's one of those things that you really need to work on getting over. And it's very true in academics as well. There's a lot of, professors and stuff who have this kind of imposter syndrome. But it's one of those things that it's largely like you have to give yourself the pep talk, like I'm good enough, I'm smart enough, people like me type of thing, right? But it is really important, and it's a real thing. Imposter syndrome keeps people from applying for jobs. It keeps people from doing things that they don't think that they're qualified for. One of the things that I like to mention to students, particularly my female students, is that on resumes, they've done studies where they have like resumes of male and female applicants applying for the same job, basically. And what it turns out is that like male applicants lie a lot more on their resumes than female applicants. Female applicants are much more honest. They're like, this is what I can do, this is what I can't do. They're just honest about it. And men are just like, yeah, I could do that. Like I could figure that out. Like I don't exactly know how to do it now, but I could figure it out. Like I'll just figure it out on the job. So they just kind of lie about it. And so what I tell my female students is do that, basically. Like don't lie, but like embellish a little bit, right? If you see postings on job websites for certain skills that you could learn, put them on there and then learn them, while you're waiting for your call about the job interview, right? You don't exactly have that skill just yet. Maybe you're not quite as good at it as you advertise, but you can be, and you should be. And the male applicants are already doing it. So to level the playing field, female applicants should do it as well. And this doesn't go for just female applicants. Men should do this as well. But, my wife is kind of funny. She I guess she said that she knew Excel on her resume and got this job. And then she calls me from work. She's just like, I got an Excel problem. I don't know what I'm doing. I don't know how to use Excel, right? And I'm like, okay, well, let's do a screen share and show me what you're doing, and here's a little article from Stack Exchange on how to do formulas and these kind of math tabulations in Excel and that kind of thing. But that's the type of thing that you're going to be dealing with. And it's I need all these skills, but people overpost in those job postings, right? I need this huge laundry list of skills. They don't exactly expect everyone to have those things. The important part is being willing to learn them. And again, there's a limit to this, right? You're not going to say that you're a full stack programmer that can do all these crazy technical things when you can't do any of them, right? It needs to be achievable. It needs to be achievable in a short time span so that you can kind of cover your own ass if somebody calls you on your bullshit, basically. But don't lie, but embellish, and you have to sell yourself, and you have to kind of oversell yourself, basically. And if you get the interview, get online, learn some tutorials, right? And actually make it true, essentially, because it can be true. And the job interviewer or the job recruiter doesn't have to know that it's not true exactly at the time that you put in that application. But if you want that great job, you got to do it. So do it. Write the resume for the, that you want and that you can achieve in short order. One of the things that I really like to mention is that time is really short. And it feels like, especially when you're in college or you're just getting out of college, that you've spent your entire life preparing for life, right? You're being educated. And then after college, life begins or something. I'm that's not really true. You're living life right now. College is a part of life. But, thinking about my own life, I feel like I was in undergrad yesterday, right? And I'm nearly 40 now, and I don't look it really, and I don't feel it, but I'm getting old, basically, and I got a kid who's running around and stuff like that. But the point is that you go from being 20 years old and in college to almost 40 in what really feels like the blink of an eye. And I've done a ton of stuff in that time. I went to grad school, I've had all these jobs and career shifts and all these things, but it happens quick. And it doesn't, I just remember being in college, damn, this has taken forever for me to get through college so I can kind of be a proper adult. But the speed at which things go, especially once you get to the point where you're getting married and having kids and those things, if you do those things, things just accelerate incredibly rapidly. And your 20s and your 30s are really your earning years, and your 40s too, but where you're really setting yourself up for your career trajectory. And that's another reason why failure is so important, is you got to fail quickly, fail fast, especially if you're going to get into a field. I want to be a nurse. My wife wanted to be a nurse. She was a psychiatric nurse in Canada. She realized that working on a psych ward is hard, it's taxing, and she got out of it. But she got out of it by the time she was 23 or whatever. a little older, 25, and then like switched. And then she's like, oh, I'm going to be a school psychologist. I'm going to deal with kids because I can deal with, psychiatric issues better in kids where you catch them early than where you're just treating them at a hospital setting or whatever. But and that's like still the same field, but like she changed her position within that field and she did it relatively early. And, also like those first jobs that you get out of college, the first job's always your hardest one to get because you have almost no experience, but then they get progressively easier. It's also much easier to look for a job when you have a job and you're kind of sought after more, I think. But getting those first couple jobs and getting up on the pay scale is going to really drastically change your lifetime earnings. So get good jobs early and really hustle a lot early. Because if COVID's taught us anything, like life is short and you really need to kind of value the opportunities, the fact that you're at Cal Poly, the fact that you're getting an online education, online now, hopefully in person soon, and also in college, you need to take advantage of the people around you and the networking opportunities and research opportunities and all of these internships and that kind of thing. That's very much a part of college. It's not just the coursework. And so, really kind of lean into these opportunities as much as you can. I did not do that as much when I was an undergrad. I was much more, focused on, I don't know, surfing and partying and doing whatever, you think about when you think about your average UCSB student, but I wasn't taking advantage of the opportunity as much as I wished that I had. So, while you're here, really try and lean into those opportunities because they're here now, they're gone tomorrow, and they're not coming back probably unless you go to grad school, which is, basically college for big kids. And I do recommend going to grad school. It is fun. And you really actually kind of like find your tribe a little bit more. You find your people who are like much more focused on the thing that you're focused on specifically, and you can dive deep on topics. So they're really important decades, and getting a master's degree is really going to help you in terms of earning, but also just like it helps you not be an entry-level person for your whole career. You can be in charge, that kind of thing. And that was one of the reasons I went back to grad school, is because I was like working in a private company. I was kind of a dead-end job, so kind of a 9 to 5. And I liked it at the time, but I was also just like, I feel like I'm smarter than the managers who are telling me what to do, right? And like, I didn't like that. Like, I have to go get a degree if I actually like want to be in charge, type of thing. And obviously I left private industry, but what is it you say you're trying to do here? And I ask this of my students all the time. I rarely get a straight answer, right? Like, what do you want to do? Like, what job do you want? And most students are like, I don't really know, right? And it's like, people have been asking that your whole life. Like, what do you want to be when you grow up? When you're a kid, you're like, I want to be an astronaut, but now it's like, okay, you really need to have an answer for this question, right? And it's good to say it out loud. It's good to talk about it with other people and talk about it with your professors and talk about it with your family and talk about it. Like, you got to have a plan. And if you don't have a plan by towards the end of college, like there's something wrong. You need to get a plan. So, so what is it you're trying to do here exactly, right? The time is now. Really lean into these opportunities. Like this is it. And especially as the pandemic is kind of winding down, we're getting back out, we're being social, and the world is opening back up. That's great. But really take it to heart. Like this, you only get one shot at this, basically, and life is short, and you'll be 40 with a kid before you know it, and things get a lot harder then. So also be very humble about what you know. I get a lot of like really cocky undergrads who are just like, they think they know more than you do, and I kind of like it because it's like, oh, like this a really cocky student here. Like, let's see how much they do know. And I really like to test them and that kind of thing, right? You go to grad school and you're humbled basically. But one of the things I was taught about teaching undergrads and teaching graduate students is always encourage undergrads and like tear down graduate students basically. So I try and do that. I always try to encourage undergrads to like, go, you're doing great, you're doing great. But like when you get into grad school, like people are just like telling you everything that you don't know, and it's most things. So, you just need to be really humble about what you know and you don't know, and don't have an inflated ego. Not having an ego is a really important thing, and just sort of keep going, and be willing to learn. Ultimately, this comes down to like your willingness to learn. So grad school may be necessary. More and more people are saying like, the master's is the new bachelor's type of thing, especially if you want to get to these higher levels in your career. And even if, you want to be a teacher, teachers with master's degrees just get paid a little bit more. Do you need a master's degree to be a teacher? No, but it might help. So, that's partly why you need to go down these dead end roads and work a corporate 9 to 5 for a couple of years, it'll inspire you to go back to grad school. It'll make you hungrier to go back to school and learn more stuff about certain things. It's totally what happened to me. It's like I left college and I was like, I'm never coming back. Like school's out forever. And then it was like I work on a 9 to 5 for a year or two, and like kind of hating it and realizing that like, my managers had master's degree. I was like, damn it, I gotta go back. I gotta go take the GRE, and that kind of thing. But I needed to go down that road. I needed to hit that dead end before I would go back. And then when I was in grad school, I really appreciated it. I loved it. And it was like, and I was happy to be there. Whereas a lot of people feel obligated, especially in their undergrad. It's like their parents are like, you gotta go to college, you gotta go to college. Like you don't really have a choice type of thing. It's like grad school is very much a choice, and you do not have to go to grad school. And so don't go unless you really want to go, basically. There's also really large differences between PhD programs and master's programs. And when I say that, I mean like terminal PhD and master's programs. Oftentimes you'll get a master's on your way to your PhD, but like, they're very different. A lot of times master's programs are much more skill focused and focused on like job skills and getting you technical abilities and that kind of thing. And a lot of GIS programs are like that. Whereas a PhD is kind of a whole different ball of wax. If you're really into GIS, look at some of these programs. University of Redlands in Redlands, California is the most expensive graduate program, and part of what they're doing is they're selling access to Esri because they're right next door to Esri, and a lot of people work at both places. And actually, the University of Redlands is a really charming little school. I was this close to working there, and I'm so glad I didn't because I like slow more. But it's a really cool place actually, and they do really good work in terms of GIS. It's just crazy expensive. University of Southern California, USC, also crazy expensive. And then you go down the list, and there's a couple links here that you can check out. These online master's programs are online or in person. University of Redlands actually is in person, and they require you to live there, like I think on campus actually, because they want you to network, they want you to be a part of this community, etc. So that's partly what they're selling. Probably why it's so expensive. But there's like Long Beach State has got a good like master's program in geography. It's awesome, right? And it's cheap, and a lot of people get good jobs out of that. Arizona State, I think it's all online, focused on tech. Johns Hopkins focused on intelligence. I heard the University of Denver has a good program. I don't really know much about it, but like there's all these different programs, and you should look at them. And and a lot of them are much more focused. So it's like a master's in GIS, but like GIS for technical applications, or for intelligence applications, or for public health, or whatever. And so just take a peek, see how much they cost, price them out, see if it's right for you. I've got a number of students who leave Cal Poly and they go join one of these programs, and I'm kind of hear reports back from the field. Some are worth more than others, but it's worth doing your research on it because it's that way to get to that next kind of step. Build your skills. Again, we're just sort of scratching the surface here in our undergrad and in these classes. So worth noting. And with that, I'll sort of conclude my little pep talk. We'll just talk about the class here for the last minute or two of class. So wrap it up, B. You're in week 9. So week 10 is going to be dedicated only towards group work. There'll be no lecture. I will post a small final exam, but it'll be hopefully kind of fun and not too taxing on your time. I did adjust deadlines a little bit. So group work is going to be done at the end of week 10, Sunday, just like everything is due. And then actually the following Wednesday is when I'm going to make all the individual projects and reports due. A couple reasons for that. We need to do peer reviews on the group reports. So you're going to watch the videos of all your peers and kind of give them reviews. And you're not going to do that for your individual reports. So you're going to get a couple more days. So focus on the group reports first, get those done, and get those out. And then you can kind of work on your individual reports with the last little bit in finals week. And I need a little bit to grade them, obviously. An idea that I had, and this is kind of up to you, and I put it out to the students if you want to do it, maybe a happy hour in week 10, actually in person, like an MDO, like we could go to Hazard Canyon, there's the sand dunes there, you get a Spooner's Cove, and just like bring a drink and just actually go and hang out outside, assuming that you're fully vaccinated. I would attend that if I could, if the timing was right, but I would actually call off class like on like next Thursday or something to do it. Or just push class back in a couple hours and make it more of an evening class, that kind of thing. But it's just an idea. I know that like the Zoom happy hours, they're kind of fun, but also they're a little sad, and they're kind of like, I don't want to do that. Like I want to sit on a computer more. But this is just an idea, throwing it out there. If students want to, if you want to organize it, go for it. I would go if I could, if the time works out. So just throwing that out there. So come to office hours in week 9 and 10. That's going to be really where a lot of this work gets done. Focus on your group work first. Ask for questions. Please ask for questions if you have them. If you like this class, we're going to do it in person next year. It'll be called Geography 441. So it'll be a different course. You'll get credit for it. And it'll be similar, but it'll be a little different. Obviously, it'll be in person, it'll be a computer lab, but it'll be a project-based course. You could always pick, some of these projects are ongoing, so they'll probably be repeated, but you could always pick a different project. You can continue your individual projects, you can work on senior projects, you can do all kinds of stuff like that. So yeah, so with that, do your evals and nice work. Thank you for being here and kind of coping with online school. I realize that it kind of sucks, but I've been really encouraged with what I've seen from the students, and I've seen really good work, and a lot of really motivated students have done great stuff, and so that gives me a lot of hope, and it also makes me like really excited to get back to the classroom. So I'm really looking forward to meeting some of you in person. I met my TA Sarah the other day, and she's like, oh, it's nice to actually meet you in person. I was like, dang, have we not met in person? Like I kind of lost track of who I've met and not met. So I'm excited to actually meet students again in person. It's time to get out from behind the Zoom lecture and get back in the classroom. So thank you for coping with it. I know it's been a hard year, but we're like light at the end of the tunnel. Everybody's getting vaccinated. We're getting back to real life. So I'm very excited about that. So with that, hopefully I'll see you in office hours. Just come by and say goodbye if you want. Like you don't have to, but it'd be nice to see you and be nice to say hello before summer. So there'll be a quiz associated with this and the last lecture, and just hit me on Slack if you have any questions. So thank you so much, and I'll hopefully see you soon in person. End it, and bye-bye, everyone.